Thank you, John, and thank you very much for organizing this wonderful workshop. I learned so much here. Also, I have to confess that when I got this invitation, I was a little bit flabbergasted because a workshop on rotating convection, I never worked in rotating convection. So I felt a little bit strange. And honestly, I came quite relatively late into fluid dynamics and magnetohydrodynamics. I had a career start which was quite unsuccessful, a little bit scattered and shattered in solid state theory and geodesy and Antarctic research and remote sensing. And then I went into fluid dynamics and I saw this terrible Navier-Stokes equation and induction equation. And I thought, my gosh, this is all terrible. And I hope that I can make a completely isothermic career with delta t equals 0. And in principle, you can do quite a lot with delta t equals 0, especially in magnetohydrodynamics. And in the last 28 years, we did quite a lot of things, mainly experiments, but also a little bit of theory. So we started with a Rieger dynamo experiment, which was indeed the very first successful dynamo experiment in the world in 1999. We went over to the various versions of the magneto-rotational instability. So with our PROMIS device in Rossendorf, we did helical and azimuthal MRI. We did also the kink-type Taylor instability, which is a m=1 current-driven instability. We did work on magnetized spherical Couette flow, which was very interesting. And recently, we did also some work on alphane waves here with liquid rubidium, which is even much more dangerous than sodium. It's really fun to work with rubidium. And so with this paper, we did it at magnetic fields at up to 60 Tesla. And we managed to cross the point where the alphane speed becomes equal to the sound speed. This is quite important for corona heating. And we got quite interesting results here. And at the end of the day, our experiment made it on the cover of PRL. And I said to my wife, if nothing remains from my brain, my fingertips will always remain in physics here because they are on the cover of PRL. Anyway, delta t equals 0 is nice. And if you are interested in all those stuff, you might have a look into this Nature Reviews Physics paper I wrote last year. But sometimes it comes back. And it came back, for example, in an experiment on the azimuthal MRI. So we have a Taylor Couette flow in the Rayleigh stable regime. And then we run a current through the middle up to 20,000 amps. And this makes a strong magnetic field. And then you get the azimuthal magneto-rotational instability. But still, even if you insulated this current in the middle thermally, you get a little bit radiation and you get a tenth of a Kelvin delta T. And this has some effect because it drives the elevator flow of now maybe a millimeter per second, which is quite comparable to the MRI structure. And then we got, depending on the radial heat flux from outside to inside or inside to outside, we got such one-winged butterflies here going up and down. And recently, Ashish Mishra, a very, very gifted PhD student of us, he simulated this, so he combined the azimuthal MRI with this elevator flow driven by temperature gradient, and he got indeed this one-winged butterflies. It was a JFM Rapids paper last year. We called it really one-winged butterflies. So we did something on the combination of MRI and convection. This was my first encounter with delta t in a way. So anyway, my talk will focus mainly on the solar dynamo and on harmonic forcings of the solar dynamo, maybe some synchronization of the solar dynamo. At the end, I will talk about a huge experiment in Dresden-Rossendorf, the Dresden precession experiment. But I felt a little bit obliged to say at least a few words about convection, and I focused a little bit what I did also in the last years. And I would like to show you a relatively new measurement technique, which we call contactless inductive flow tomography for liquid metal convection. And I will speak also in this connection about helicity oscillations. So let's before I start, I have to say this will not be a very systematic talk. If you are really interested in harmonic forcings, libration, precession, tides. So we had a wonderful talk this morning by Michael Lebar, and here's a great paper by him and collaborators from 2015. And here is more by Langdo, a paper on application of all those forcing for the Earth. So if you are interested in more general things, please consult those wonderful papers here. Okay, let me come to liquid metal convection. Tobias Vogt is our leading guy in convection. He was also here at UCLA. You did great work at large gamma. And one of the most important things which was detected by you guys together with Tobias was the so-called jump rope vortex, a new structure which is going like this and which seems to be quite a basic flow structure in gamma large cells. There was a Proceedings of National Academy of Science paper here by Tobias Vogt and you guys. And we do now quite a couple of experiments with gamma 5, gamma 25. There is a lot of activity going on here, and I don't want to speak too much about this. What I'm more interested in is small gamma 1/2. Here is a big cell with a large radius filled with gallium indium tins. This is a real expensive thing, maybe some $150,000 or so just for the gallium indium tin. But you can make nice experiments, and this was done in a PRL paper by Felix Schindler and colleagues. And there was some need for some correction in a erratum here, but what they found is indeed here the Reynolds number and the Nusselt number with some typical scaling, and it's more or less in agreement with the Grossmann-Lose theory for small magnetic Prandtl number. So what I was interested here is, could we see the flow? Of course, you can do. You can measure temperatures, you can measure with ultrasonics, but could we get perhaps a complete flow structure by some magnetic tomography? And I go back for one slide to one of the formulations of dynamo theory, which we developed in 2000 with Karl-Heinz Redler, and then applied to quite a couple of dynamos in finite cylinders, in cubes, in rectangles, whatever. And this is based on the so-called integral equation approach. This is basically Biot-Savar's law, and you have to solve it as an integral equation, but still you need the electric potential at the boundary. You have to solve this two-dimensional boundary element equation here for the electric potential. But with this method, you can nicely compute dynamos. It's the integral equation approach. Even below the threshold of dynamo action, if you apply a magnetic field to a flow U, you will get some induced magnetic field. So we had yesterday the talk by Simon Cabanis, this morning was something. So if you apply a magnetic field and you have a inducing velocity U, you get an induced magnetic field here. And now you can try to infer the velocity U from the induced magnetic fields. So we did the mathematics in quite early papers, 99, 2000, and then we had a first paper in PRE where we had a propeller-driven flow here, and we drove it up and drove it down, and then we applied two different magnetic fields, measured at a couple of measured the induced magnetic fields at a couple of positions here, and then inferred onto the velocity inside. So this worked quite nicely. And with this, we went now to the gamma 0.5 convection cell. This was mainly done by my colleague Thomas Wondrak. He did really a lot of work in get this running. You apply something like 1 millitesla, and the induced magnetic fields are of the size of some 10 to 50 nanotesla. So you have to be very accurate. You can do it only overnight. You have to compensate the Earth's magnetic field changes. There's a lot of technology needed. But at the end of the day, we use 7 times 6 flux gate sensors here around. And what you get is more or less a very nice picture of your flow structure of this Rayleigh-Bénard. The main result of this is that we have a complete loss of coherence. We have a transition between single roll, double roll, triple rolls. So it's quite chaotic, these transitions, and we can see it very nicely with this magnetic tomography. As a dynamo guy, I'm always interested in helicity. So the scalar product of velocity times vorticity here. And we did look for the helicity in those flows. These are really experimental results here. And yeah, while we have a permanent transition between single roll structure, double roll structure, triple roll structure, you get in those areas here where you are here within the double roll structure, for example. The Reynolds number is relatively constant, but what you get is indeed helicity oscillation. So it's going like this. And we can see it, indeed, we can see it in numerics, but also with this contactless inductive flow tomography. You see here how the helicity is changing for this double roll structure. The same applies here in the area where the single roll is dominant. You see here it's more or less the famous sloshing motion, which is going like this, and you can also identify it by the magnetic tomography. Okay, speaking about helicity, and I'm a little bit anticipating what I will later tell you about the solar dynamo synchronization. We had the idea, if we have some intrinsic helicity oscillations, what about the action of tide-like forces when they act on this helicity? What happens then? And indeed, we did one experiment. This is now a gamma 1. And you know, you have the large-scale circulation, which is typically undergoing sloshing and torsional in a combined manner. And the sloshing is definitely connected with the helicity oscillation, right? You have it's going around your omega, and then it takes a velocity here, and this is intrinsically a helicity oscillation. And what we did then, we put this flow into 2 coils, and we applied a current of 24.5 Hertz, and we modulated this current here. And if we take only the flow from this tide-like structure, you get 4 such rows. Here is a tide-like force. It's very similar to, Michael, what you have done with your mechanical forcings. We do it electromagnetically here, relatively similar. And what you get then, this is a time average, a 4-like structure, and then you get indeed a synchronization of the helicity. This is what we observed, and we did an experiment. It's a little bit busy. So we put such a gamma equal 1 cell into our multimag system. Here, 2 of the coils of the 6 coils were used in order to drive this. And indeed, at a certain threshold of the current, we observed synchronization of the helicity. Okay, and this brings me now to the solar dynamo problem, where I believe that helicity oscillations play a quite important role. And I think we learned from talk of Nick on Wednesday, solar dynamo theory relies basically on 2 effects which were invented by Eugene Parker in the 50s. You have here the omega effect, like a spoon in a cooking vessel with spaghettis. It's winding up the spaghettis in such a way, but you still need some alpha effect to replenish the poloidal field. And if you put them together, you get a dynamo loop and you get your solar dynamos. This is more or less the standard since many, many years. People are doing a lot of simulations. So here is maybe not the newest one, Carac and Mark Misch. You see, you can get, in principle, your butterfly diagrams. There might be better simulations now. And you can, if you fix your parameters appropriately, you can get your 22 years Hale cycle. No problem with this. And most people are happy and try to improve it. But there are a few crazy people, among them me, who thought there might be a problem with this picture here. Because if you look into the sequence of sunspots, you might get the impression that they are clocked by whatever process. And if you look more carefully, it looks that as if the Schwabe cycle is 11.07 years, and this number shows up again in the planetary system by the beat period of the 4 permutations of syzygies of the tidally dominant planets, which are Venus, Earth, and Jupiter. This sounds very, very weird, given the very small tidal forces of the planets. And there's a lot of fighting on, yeah?
I think maybe I just didn't understand. Could you explain that just like 30 more seconds, or this locking that you're describing?
Sorry?
This clocking thing.
I come to this in a minute.
Okay,
I will show much more about this, okay? So there is a lot of fighting here, a couple of papers. So we get really some heat from Ulrich Lodner-Taff and Weishar. And this is very, very surprisingly emotional topic. And I do now something which might be even a little bit illegal. I got yesterday the refuse of my rejected ERC grant. And one of the referees wrote, this is seriously flawed and is indeed akin to numerology. And I do not exhibit the scientific rigor that is required to successfully execute a scientific project. So if you think you don't want to be exposed to numerology and astrology, you might go now. It's good. Anyway, so we started in looking into this topic by taking quite old data of the solar cycle by Scobie, who did a lot of work taking aurora borealis data. And if you take them here and you take again the maximum Venus-Earth alignment here, you see it's essentially one line. Now you can subtract the linear trend and you get the so-called residuals over 1,000 years. And you see that those residuals here, they are wiggling plus minus 2 years, but not more. They are never going away. It's right. It's really, really impressive. And then, if you take those residuals, you can define a measure which I called Dickey's ratio, because it was done the first time in this paper by Dickey in Nature. You can take the variance of those residuals over the variance of the difference of 2 subsequent residuals. And for a normal random walk process, this goes with n over 15 in the limit. And for a clocked process, it goes to 1/2. So you can really take the data and try to figure out, is it a clocked process or is it a random walk process? It's a very nice measure. And we analyzed Scobie's data and we found it's much more close to a clock process, right? The point is only, are those data valid? And there was a lot of discussion in the last years. So we were heavily criticized by Ulrich Lodner-Taff, and Scafetta wrote a paper against, Taff back. And then there was a paper two years ago by Weishar, Cameron, Schüssler here, and they claimed no evidence for synchronization of the solar cycle by a clock, and they claimed that they have found very high statistical significance for their claim. There is no clock. And together with Jörg Beer, we were looking into the data, and there's really a problem with the data, because they used C14 data. And if you use C14 data, you get here a little wiggle at 1845, which looks like an additional cycle. But there is no additional cycle there. We have good observations since Schwabe's time. There's no cycle at this point. Weishar et al. Did not care about this. They simply used it. And of course, if you smuggle in one additional cycle, you destroy your clocking process, right? And we wrote a paper, no evidence for absence of thermodynamic synchronization. Sent it to A&A, and it was in a half an hour rejected by the editor. It was a little bit weird.
What does that mean, no evidence for absence?
No evidence for absence.
My question stands.
Oh, okay. So then we sent it to solar physics, and it was more or less quickly accepted here. There is a second, apart from the last millennium, there is a second indication for phase stability in clocking, which is coming amazingly enough from the early Holocene, from algae data in Lake Holzmar in Germany and also in Greenland. This is a paper by not very much cited, Heinz Voss et al., 2004. They analyzed algae growth data. And apart from some problem here, which has to do with the biological optimality criteria of algae growth, which is really a little bit tricky, but what they claimed is that you had a phase-stable solar dynamo over 11.04 years, which is hardly distinguishable from our 11.07 years, given the 90 cycles that we have here. So there's a complete different time span in the early Holocene where you get the same result, essentially. This is really amazing. I don't claim that we have perfect evidence for clocking, but I would say we have enough evidence that it might be worth to look for a possible mechanism which could explain it. And this we did. I showed you for the Rayleigh-Bénard this helicity oscillations for the double roll structure, which is going like this, right? And originally, our motivation to do all this work had to do with the Taylor instability, which is important for liquid metal batteries, or maybe not so much, but we started with this in liquid metal batteries. It's a current-driven instability. And yeah, here, it should, you saw it perhaps. It's like this. And we notice that we have here an intrinsic helicity oscillation of the Taylor instability, which is very reminiscent of that of the Rayleigh-Bénard flow with a double roll structure. It's very, very similar. And we thought, oh, that's interesting. So we applied a little forcing here, m equal 2. It's a tidal forcing. And we noticed what you get is a huge resonance at this frequency here. So you have your intrinsic frequency of your helicity oscillations, and if you go with the appropriate frequency of your tidal forcing, you get a wonderful high increase of your helicity oscillation, and this means of alpha. You see it here, this is without excitation, but you can excite it very nicely. So we put this into, this is really very, very simple. It's an ODE, the simplest alpha-omega dynamo you can imagine. We put it here into such an alpha effect, and what we got is indeed parametric resonance, and we got a 22.14 Hale cycle with this method. This was the first paper in 2016. Yet, there's a problem here, and this was pointed out rightly by Henri-Claude Nataf and Jonko. If you look more carefully into the spectrum of the tidal potential, what you see is you see nothing at 11.07. There is no peak. So this original idea that we have the direct driving of this alpha effect on the time scale of 11 years does not work. So, and this puts into question all our previous works that we had here. And so we decided 2 years ago to focus on those shortwave tidal peaks. And these are coming from the two-planet spring tides of Venus-Jupiter, Earth-Jupiter, Venus-Earth, which are 118 days, 199 days, 292 days. So we focused on them. And this brings me to my first part of the solar dynamo. It's the Rieger periodicities. There's a paper by Rieger in 1985 who observed in different solar features a period of 154 days. Since that time it's called Rieger period, but there are also other ones. And if you look more carefully in recent data, here is Virgo, Satire, whatever, you often find something like 120 and 190 days. And so here, for example, north and south, it's even different. It's a little bit messy, but what we have signals in the Rieger-type timescales between 100 and 200 days, which I find quite interesting. And now, there's a lot of activity going on by Moussoumi-Dikpati and Zakharashvili, McIntosh in Boulder, who are connecting these Rieger-type periods with magneto-Rossby waves at the tachocline. We heard about the tachocline, and we indeed have those Rossby waves here at the tachocline. At this point, Gerrit Horstmann jumped in as a very gifted mathematician, and we decided, let's check Rossby waves, magneto-Rossby waves, and look what tides are doing with Rossby waves. So we used a shallow water approximation. It's more or less the Dikpati formalism, but what we included is some dissipation term and a tidal forcing with m equal 2. And what Gerrit got, together with Georg Mamatsashvili, Zakharashvili is one of the co-authors. I hope that everything is correct, because Moussoumi was a referee, as far as I can think. And we got an 8th order differential equation here for the velocity, and this can be solved more or less analytically. And what you get then, if you take the first combination, which is Venus-Jupiter, you get, depending on a dissipation parameter, which is not that well known, you get velocities between 1 and 20 meters per second for your Rossby wave. Let's go a little bit further. This was the 118 days. Let's go to the Earth-Jupiter. It becomes even larger at some 50 meters or something here. And then you get Earth-Venus, you get even 100 meters per second. So those Rossby waves, they represent a wonderful resonance ground. They have periods which are amazingly nicely correspond to those 3 tidal forces. And they can react on these tidal forces here. Mercury is a little bit special, so it's not very strong. Okay, so let's assume that we have brought enough energy from the planets into the magneto-Rossby wave system with 3 different frequencies. The question remains now, where does the 11 years come from? And this is the old idea by Nicolas Scaffetta, who showed that this 1107 can be described in such a way with the periods of Venus, Earth, and Jupiter. And then he claimed it's a combination of the second harmonics of Earth, Jupiter, springtide, and third harmonics of Venus, Earth, springtide. Then you get exactly the 11.07 years, right? You see it here, this difference. The point is only, what the hell should the second harmonic or third harmonic of those things have to do with the physics, right? This is really a question. So we tried to go over from mathematics to physics, and we asked the following questions. Imagine you have your 3 waves, your 3 Rossby waves with the 3 periods I mentioned already. And let's assume that any relevant dynamo action, it might be alpha, it might be a change of the zonal flow, it might be some meridional flow, will be some sort of a quadratic functional of the sum of the 3 waves. And what you get is a beat period of 11.07 years. It goes even a little bit further, that even the axisymmetric part of this has still a period of this 11.07. This does not apply, we talked about this. If we skip one of the waves, then we don't get to 11.07 years here. The deep reason is that this comes from Scaffetta's notion of orbital invariance, that this action, the beat period, does not depend on the angle phi. So it's independent. That's why your axisymmetric part of this gets some 11.07. It might be alpha, it might be zonal flow. Okay, this is quite busy. What we did together with Laurent Jouve from Toulouse is a quite simple 2-dimensional alpha-omega model with meridional circulation. So what we used is we used here the usual omega profile. We used here a typical meridional circulation. Then it's not really Babcock-Leighton. We use some alpha effect in the convection zone, right? And we made out of this a normal dynamo which might have a period of, say, 18 years or 25 years or whatever. And then we say that due to the joint action of the three Rossby waves, we get a little kick of C alpha every 11.07 years, and this is living here in the tachocline. And we put this as a force ingredient into our model. And what we learned from this, indeed, we get a reasonable butterfly diagram, but what is more important, depending on the strength of this periodic alpha, you get a parametric resonance and you entrain your entire dynamo to the 22.14 years. The question remains, how much alpha do we need? And the answer is we need some DC meter per second. In view of the fact that the Rossby waves might acquire velocities between 1 and 100 meters per second, I believe that an alpha effect of DC meter per second might be reasonable. At least it's not too far away. Okay.
Frank, how would you get it?
Sorry?
How would you get it? How would you get the DC meters per second?
We took this model with relatively normal parameters. All conductivities and omega and meridional, these are real numbers. And then we were asking, we took some 1.3 meter per second here in this alpha. One might play a little bit. And then we were asking, how much do we need here? It's in physical parameters, right? And this is indeed DC meter per second.
How much the result change with the profile of the meridional circulation?
Always a little bit, of course. The point is that we must, in this very model, we must not go too far away, so maybe some 10% or so, but all those details might change, right? But we took a reasonable meridional, but I know what you mean. If you have multiple cells, it might be.
So it requires 3 frequencies.
Yes.
What are those? What are the periods of those?
It's 118, 199, 292, which are the two-planet spring tides of Venus, Earth, Jupiter.
So what are those in years?
Well,
Those are in days.
you might. 118 is a third of a year.
Okay, so
Okay.
These are all less than a year.
Sorry?
These are all less than a
Yes,
year.
yes, 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 yes.
But can we get DC meters per second from these tidal frequencies only on the sun's time?
I come to this a little bit later, alpha and the basic frequencies. This is a tricky thing. But I wanted to say we have a reservoir of maybe some 20 meters per second, say, and we need a little bit alpha of DC meter per second, right, for synchronization. It goes a little bit further. We have not only the tidal forcing, the sun is also undergoing a rosette-like motion around the barycentre of the solar system. And there's a lot of work done by Jim Shirley, who's here in the audience, who did a lot of work on this spin-orbit coupling modeling. And this has a main period, not only, but a main period of 19.86 years, which is coming from Jupiter and Saturn. Now comes really a tricky point. So if we take the tidal forcing and we say we have the first synchronization here to this value, and we have a second one, which we admittedly parametrized in our dynamo model. This is really not well understood. But if we put it somehow into the dynamo model, you get a second synchronization to a Suess-de Vries-like period of 193 years. You see it here. It's reddish, bluish, reddish, bluish. And maybe now comes no, not yet. A little regression to a 1D alpha omega model. I played a lot with this one-dimensional model. It's much simpler than the 2D model anyway, so it's here. And here's maybe my most important slide for today. So here is the spectrum which comes out of my model. with only Jupiter and Saturn, all planets with a little bit noise, and here with this dominant 193. And here something Gleissberg 90, and here 50 something. And then 1.5 years ago, I stumbled about another paper by those guys, Voss et al. And Prasad, 2004 again, who analyzed the yearly sediment thicknesses in Lake Lissan in Israel, which is a mirror of the precipitation at this time. At the time, 20,000 years ago, for 8,500 years. This is a wonderful stack of data. And what they got is this spectrum here, 192. Here 90, 57, this one. And I was really shocked by this agreement here. So I think this might be something. Okay, another thing which I did really in the last 2 weeks was...
Can I just add, what's the point of that correlation?
Sorry?
What's the point of that correlation?
2 points. So one is, we have this spectrum of the solar dynamo, and it agrees with precipitation data in Lake Lissan. The point is it really the solar dynamo, first? And second, if it is the solar dynamo, how does the influence on the climate work? This is not my topic today. It would need another few hours. It seems that there might be some stratospheric-tropospheric coupling coming from ozone changing from UV and stratospheric heating, then all this, whatever, going down. This is a nightmare, but there are ideas that solar influences the path of the cyclones in the North Atlantic, and they decide whether they come to Israel or not. But this is a very, very long topic, right? So, okay, bimodal field sunspot distribution. There's a paper by, or quite a couple of papers, Nagovitsin and so, who showed that there might be 2 typical peaks of the sunspot intensity. And there's one explanation, there might be more, you guys might know more, from Georgieva, who said this might have to do with, so in one version you have the meridional circulation, Babcock-Leighton, it brings it back, but there might be shortcuts by diffusion, and this might give you 2 maxima of the sunspot cycles. So what we did, we put all this in our model. It's again the one-dimensional model, and what we saw here, the green one is the B phi, the violet is the 50 times the poloidal field. This one is alpha with the 2 components, and you see already here this yellow one, sorry, it's a little bit, I should have chosen different colors. It's quite small, you need not very much alpha in order to entrain the entire dynamo. It's really only a few percent to entrain it. And what we get is here such a sort of second hump. And you see it here. Maybe I should show a better one. These are the parameters which I just have shown. Here you see a very robust feature of a second maximum. And this is a very robust feature which simply comes out of the synchronization. To wrap up this part, we start from a conventional alpha-omega dynamo without synchronization, but a natural period around 20 years. Then we have the tidal trigger of 3 magneto-Rossby waves. They form a beat period of 1107 in the tachoclinic alpha. This gives us the first synchronization. Then we have spin-orbit coupling, James Shirley, which we do not completely understand. This gives a second period, Suess-de Vries. There might be some transition to Bray-Hallstatt. This is another story. I have some slides, but I don't want to go into this one. So the general principle is that we harvest the energy on the shortest possible timescales. And these are a few hundred days. And all the dynamo periods emerge then as beat periods. So these 3 tidally triggered Rossby waves gives Schwabe-Hale, and Hale and barycentric motion gives Suess-de Vries plus Gleissberg. I would like to point out one thing. this model is highly self-consistent in the following sense. You would not get the 193 Suess-de Vries if the 22.14 were not phase stable in the first place. If you would like to have a beat period, both periods must be phase stable. So this is a backward-reaching argument also for the phase stability of the Schwabe-Hale cycle. Oh, I have to speed up again. So of course here are different problems which we would like to see the alpha effect coming out of the Rossbys. We have to better understand Jim Shirley's spin-orbit coupling model. Here are quite a couple of things. There's a paper, you mentioned Moffat. There is a paper by Avalos, Zuniga, and Redler who computed alpha from Rossby waves. We should go into this a little bit more, and we should better understand the spin-orbit coupling here. And we plan 2 experiments again with this multimag here, where we excite 3 different waves with tidal forcings, and we would love to do an experiment on the spin-orbit coupling. Now I have really to speed up. Going back to the Earth, you might have heard Earth is is a steady magnetic field, but sometimes it's undergoing reverses. But there is some sort of regularity here in the sense that one of the Milankovitch cycles, at least, this is the ellipticity of the Earth, which is 95 kiloyears, is visible in the statistics of the reverses. In the sense of a stochastic resonance, you have a peak at 95 kiloyears. You have at 2, 3, 4, 5 times 95 kiloyears. So there seems to be always a sort of kick coming from this ellipticity changes of the Milankovitch cycle. Maybe I skip this here and go directly over now to our precession experiment. So essentially, we have 2 motivations. One is coming from this not perfectly understood spin-orbit coupling effect, where a similar Poincaré force appears as in precession. And here is the Milankovitch cycles of the Earth. So we decided 15 years ago to go to build a huge project, a precession-driven dynamo. This is called Dresden. It's a new building with 12 tons of sodium in the inventory. So we would like to, we built this precession-driven dynamo, but also MRI experiments, Rayleigh-Bénard perhaps. This is the general scheme. So here's a machine. The heart is 2 times 2 meters, a cylinder, supposed to rotate with 10 hertz and to precess with 1 hertz. Here are all the technical details of this machine. We did in the last years a lot of theory and a lot of experimental studies with a 1:6 downscaled water experiment, which was extremely important. And what we got in the last years is a quite reasonable agreement for different nutation angles of the arising modes. So the first mode is a sort of Kelvin mode, which is coming up here, the m equal 1. And you see it goes up here, but then it suddenly breaks down. And this breakdown is coming from a Rayleigh instability, which appears here. This is really, it becomes Rayleigh unstable, and then this m equal 1 breaks down. And what is really important for the dynamo is what we call the M0K2 mode. This is a double vortex structure like this. This is very good for the dynamo. This appears only in a relatively narrow regime, exactly there where the flow becomes turbulent and unstable, a little bit before. So André Giesecke did a lot of work in hunting for the dynamo. We think that we should get a dynamo at 430 Rm. Technically feasible is hopefully 700, so we have some safety margin, but it's not so large. So we are really at the edge of technical feasibility here. Again, this is the machine, 2 meters times 2 meters, 8 tons of sodium are here. Magnetic Reynolds number 700. This motor is a 1 megawatt motor, which is supposed to drive this 10 hertz. The problem with such a machine is you get a huge gyroscopic torque, which in this case amounts to 8 million Newton meters. This is a large number. This is like 400 tons here, 400 tons here. This is pulling up, this is pushing down, and this is going around with 1 hertz. So this is really a lot of load onto the basement. And for that reason, we had to make a lot of take a lot of measures. Here you see how we drilled 22 meters into the bedrock, some 7 pillars going down. Here you see the construction of the ferroconcrete basement. I go a little bit quickly through the construction of the machine. Here you see this big underframe. Here's a ball bearing 4.5 meters diameter. Then we have the so-called pylons, and here the traverses with which we can change the nutation angle. So here we did a test assembly of everything, brought it then into our containment, which we need for safety reasons for liquid sodium. One of the tricky things is we need a rotary connector for the 1 megawatt of power, but also for the oil, for the lubrication oil, for the 2 bearings. In both directions, right? So this was a quite tricky thing, this rotary connector. It's not so easy to buy one in Germany. So here's again the vessel. You see it here. We made a pressure test. We have typically a centrifugal pressure of 20 bars, which is fine. It's not a big issue. So 3 centimeters wall thickness, it can easily withstand. So we did a test here with 35 bars, and then it came to Rossendorf from the company in Chemnitz on 2020. Here it was qualified. You see it's quite complicated part here with some bellows for thermal compensation. Well, then came last year, January 17, there was a big wedding between the frame and the vessel. So we brought the vessel into the frame. Everything went quite smoothly. We were absolutely happy about this. So here it's done. Ready to go, and then sorry, this is not true. So the spiggle is not true. It's just HDMI, I guess. So it's not true. Should be funny, but vibration, right? So, anyway, so this was our first experiment in November 22. Here you see our colleagues looking in. It's a control room. I was very happy that we observed. Perfect. I was very happy that we observed this transition between laminar and turbulent. Approximately, it's the same Poincare number, this means precession ratio, as predicted from the small experiments. This was not completely clear. You get here, at this precession ratio, you get up, and then you get down with some hysteresis. You see here, there's a little hysteresis. It's a difference when you go from laminar to turbulent and from turbulent to laminar. It's not the same point. We were quite happy, and we celebrated a little bit this little event. Now we have a problem. We have to bring back the cylinder because there was some spilling out of oil from one of the bearings. This was really a fault of the company. So it will take another 8 to 10 weeks. So I just reversed the video from. We have to bring it back. It will appear in the next weeks. But I'm really a bit frustrated that we lose again 2 months or 3 months with this. Okay, with this, I'm mostly done. The sodium system is ready. So we will do a few more runs with water, but hopefully in 26, hopefully we can do sodium experiments. And with that, I'm more or less just in time ready with my talk. Thank you very much.